guys, we are at the end of chapter 3. That means there will be a chapter 3 test next class. So we're going to do the topic review that is in the end of chapter 3 in our textbook. You can get this out of the textbook on page 143, 144, and 145 and show your work on another piece of paper. Or you can upload this document and write on this document itself. Either way, but make sure you show your work and upload your work. And make sure you submit it before the test, because this is how we study for the test. So it says, what are the properties of 4 types of rigid motion? Okay, so what are the properties of 4 types of rigid motion? So we did reflect, or reflection, we did translation, and we did rotation, and then we did combinations. So one of the combinations was glide reflection. So that's kind of these together. So translation is when we add or subtract to either X or Y, or sometimes both. Rotation is when I usually, if I'm moving from the quadrants, right? So I might move from quadrant 1 to quadrant 2 if I'm going to rotate 90 degrees counterclockwise. Does that make sense? So again, if I'm a point here and I rotate 90 degrees, then now I'm here. Notice I went from quadrant 1 to quadrant 2. So rotation's moving from different quadrant to quadrant. Reflection is when I flip over some line, right? I flip over some line, and the line between my new line and my old line is the perpendicular bisector. And so that's what we've been reviewing. Okay, so that's kind of just those are some properties. There's other things that are properties, but those were some of the properties that we talked about this chapter. Okay, so let's look at some of our terms. It says, let's see, the result of a transformation. So before I transform it is my pre-image, and so after I translate it is my image. So I'm going to put image here, right? Yeah, what else looks good? Oh, this one's good. This one, reflection, translation, rotation, and glide reflections are 4 types of rigid motion. So that's kind of, question 3 is kind of the opposite of question 1. All right, so that's rigid motion. A line that a figure is reflected across so that it maps upon itself. So that's the line of reflection, or maybe the line of symmetry. Both of those sound really good. So I can just move a point over here. That's my line of reflection. But yeah, if it's going to map upon itself, I think I need that word symmetry to be part of it. So I'm going to put line of symmetry. All right, what else I got here? So a transformation about a point with a given angle measurement. So that sounds like rotation. So most of the time, if you look at our notes here, this point rotated about the origin. So usually I'm rotating it and I'm given some type of an angle. So that rotated 90 degrees counterclockwise, right? So that describes that first one. A composition of a reflection and a translation. Cool, that's our glide reflection. A set of points that a transformation acts on. So the set of points that a transformation acts on sounds like my pre-image. Those are all the points that are going to be transformed. So I'm going to call that pre-image. Okay. Nice. Right, so let's take a look at 3.1. So if I look at 3.1 here, it states, rigid motion is a transformation that preserves the lengths and angle measurements. A reflection is a transformation that reflects across a line of reflection such that the image of point A is on M is A. For a point B not on M, line B would be the perpendicular bisector. So that's similar to what we summarized. And we know that reflection is a rigid motion. Okay, so we talked about this a little bit in class. Notice point A flipped over this line would land here on A prime. Now I'm using the phrase perpendicular because if I connected that line, it would make a 90-degree angle. And I'm using the word bisector because it looks like that line got cut in half. And so that's how we flip stuff over a line. So this example means they already did it for you. If I take the brown triangle and I flip it over the red line, I'll end up over here by the blue triangle. All right, so here's my answer. That's the reflection of the brown triangle over the red line. Does the transformation appear to be rigid motion? Okay, so that means that in order for it to be rigid motion, the lengths are preserved. So DE has to match DE, EF has to match EF, FG has to match FG, and DG has to match DG. So those all look good. Now let's double check our angles. So our angle measurements have to stay the same. So this angle here, angle E looks the same, and F looks the same. So I'm feeling pretty good there that I've got rigid motion. So I'm going to say yes. Angles and lengths are kept the same. All right, so looking here at exercise 9 and 10, it says take the vertices here. What are the coordinates of these new vertices if I reflect across the y-axis? So yeah, let's take a look at some of our notes. So if I reflect across the y-axis, notice if I reflect this point over the y-axis, any coordinate would be negative. It's going to turn x negative but keep y the same. So, okay, let's go back. So we referred to our notes. So let's see. H is -3, 2. J, -1, -3. K is this. So my rule was when I reflect over the y stays the same, but the x changes sign. Okay, so we can do that here. Our y needs to stay the same, so I can just kind of copy down my y. But my x has to change sign. So this -3 would turn to a +3. A -1 would turn to a +1, and a +4 would turn to a -4. So there's my answer. To number 9. Now it says, what would be the coordinates of the vertices if I reflected over the x-axis? So let's look at this rule to the x-axis. So if I flip over the x-axis, notice that this coordinate would turn to that. So it looks like the x now is going to stay the same, and the y is going to change sign. X stays the same, y changes sign. Okay, good thing we took those notes. X stays the same. So x stays the same. -3 stays -3. -1 stays -1. 4 stays 4. And the y changes sign. So this y2 is now -2. The -3 is now +3. And the +3 is now -3. All right. So there's my coordinates after my reflection. Now to review, it says, communicate precisely. Given the coordinates of 2 points and the equation of a line, how can you check that one point is the image of the other point reflected across the line? All right, so we might have to draw a picture here. Given the coordinates of 2 points, so let's just kind of randomly make 2 points, here and here. Given the coordinates of 2 points and the equation of a line, so let's say the equation is, I don't know, y = 3. So I'm given 2 points and I'm given the equation of a line. How can you check that one point is the image of the other point reflected across that line? Okay, we did talk about that. So it looks like I have a little bit of room up here for number 11, or again, if you're on notebook paper. So we said if the equation of a line is y = 3, for instance, then x will stay the same. And the first y value and the second y value will add together and divide by 2 and equal this y value, 3. They'll average together to make that line because it's the midpoint. So that would be one example. Now, it would be slightly different if it was the equation of the line was x, then it would be x1 plus x2 over 2 would equal whatever value that number is. Cool. Okay. Now let's go to, let's actually stop the video and we'll open the next one on the next.